In this video, I shall present the concept of reversible isothermal expansion of an ideal gas and show how it leads to the maximum amount of work being performed by the gas. We start with the ideal gas equation, PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the quantity of gas measured in moles, R is the ideal gas constant equal to 8.314 joules per Kelvin per mole, and T is the absolute temperature measured in Kelvin. We can rearrange the ideal gas equation to calculate the pressure of a gas. P equals nRT over V. Now let's consider 1 mole of an ideal gas at 298 Kelvin. Substituting these values into our equation for pressure gives P equals 2,477.572 joules divided by the volume. Using this equation, pause the video and calculate the pressure for 1 mole of an ideal gas at 298 K at the following volumes: 1, 3, 5, 7, 9 and 11 meters cubed. Make a list of the volumes and their associated pressures. Once you have done this, unpause the video. Okay, so welcome back. You should have calculated 2,478, 826, 496, 354, 275 and 225 pascals respectively for the 6 volumes mentioned. If you didn't get these answers, don't worry overly much now, just write them down. Keep this list handy as you're going to need it. Now imagine this 1 mole of gas at 298 Kelvin is stored in a cylinder with a frictionless, massless piston, exactly the same as we used to determine expansion work in the last lecture. If the external pressure is 2,478 pascals, then the gas will occupy a volume of 1 meter cubed as per the calculations you have just performed. What we now need to consider is what happens if the external pressure is suddenly dropped from 2,478 down to 826 pascals. How will the gas react to the pressure drop? The answer is that the gas will expand by 2 meters cubed to occupy a new volume of 3 meters cubed, again as shown by your calculations. The graph shows the pressure of the gas against its volume. As described, the gas occupies 1 meter cubed at 2,478 pascals of pressure, shown by the red dot. When the pressure suddenly drops to 826 pascals, as shown, the gas will quickly expand to a volume of 3 meters cubed. As the gas expands, it is working against the external pressure of 826 pascals. So the expansion work done is P delta V, or the area of the orange rectangle, i.e. 826 pascals multiplied by 2 meters cubed, which equals 1,652 joules. Now suppose the external pressure is further dropped to 496 pascals. Your calculations should show that the gas will quickly expand by a further 2 meters cubed to occupy 5 meters cubed. As the gas expands, it is now working against the external pressure of 496 pascals. So the expansion work done is the area of the second orange rectangle, i.e. 496 pascals multiplied by 2 meters cubed, which equals 982 joules. Further drops of the external pressure to 354, 275 and ultimately 225 pascals will result in 3 further 2 meter cubed expansions of the gas to 7, 9 and finally 11 meters cubed. The work performed during these expansions, in each case, is equal to the area of the orange rectangle swept out by the expansion, i.e. 354 pascals multiplied by 2 meters cubed, or 708 joules, 275 pascals multiplied by 2 meters cubed, or 550 joules, and 225 pascals multiplied by 2 meters cubed, or 450 joules respectively. The total work done by the gas in its expansion from 1 to 11 meters cubed is the sum of the 5 bursts of expansion work, i.e. 4,342 joules. All 6 points during the expansion are now shown on the graph. You can see that they all fit the ideal gas equation as they lie perfectly on the curve P equals nRT over V. Given the gas is performing work as it expands, the system is performing work rather than work being done on the system, and so the work done on the system W on is negative and equal to minus 4,342 joules. Okay, so hopefully the quantification of the work performed during this expansion now all makes sense. But how could we change the expansion in order to make the gas perform more work? The answer is to drop the pressure more gradually from 2,478 pascals down to 225 pascals. If the pressure is dropped so as to allow the gas to expand from 1 to 11 meters cubed in jumps of only 1 meter cubed each time, instead of 2 meters cubed, then in the 10 expansion bursts, the gas will perform a total of 5,004 joules of work, and the work done on the system, W on, is minus 5,004 joules. If we persist with this idea and allow the gas to expand in 20 0.5 meter cube bursts, then it will perform 5,428 joules of work, and W on equals minus 5,428 joules. Notice how the total area of the 20 orange rectangles is becoming a better and better approximation to the area under the curve of P equals nRT over V. 40 expansions of 0.25 meters cubed leads to W on being minus 5,672 joules. 80 expansions of 0.125 meters cubed leads to W on being minus 5,803 joules. And yes, I did work out the expansion work of each one individually. If we allow the gas to expand by infinitesimally small amounts, then this is called reversible expansion, and W on is minus 5,941 joules. This is the maximum possible work that the gas can perform, and the work done is represented by the area under the P equals nRT over V curve. Obviously, a process of infinitesimally slow expansion would take an infinitely long period of time, and thus reversible expansion work is only a theoretical, if extremely useful construct. W on for reversible expansion is calculated as follows. W on is minus P delta V, but PV equals nRT, which can be rearranged to give P equals nRT over V. So, W on equals minus nRT over V dV. If we now consider expansion from an initial volume Vi to a final volume Vf at constant temperature, then W on equals minus nRT times the integral between Vi and Vf of 1 over V dV. The integral of 1 over x dx is a standard integral quoted as log x plus c, so the integral of 1 over V dV is log V. Substitution of the limits into the equation and grouping of the logarithmic terms using the logarithmic identity shown yield equation 5, for the work done on the system during the reversible isothermal expansion of an ideal gas. W on equals minus nRT log Vf over Vi. Substitution of the values 1 mole, 8.314 joules per Kelvin per mole, 298 Kelvin, and expansion from 1 to 11 meters cubed leads to the aforementioned value of minus 5,941 joules for W on. In summary, reversible expansion is an infinitely slow theoretical construct, but it is extremely useful as it enables determination of the maximum possible work that can be done by an expanding gas. You can imagine trying to optimize steam engines, this was an incredibly important property. In the next lecture, we shall look at heat capacities